So are you able to hear? Are you able to share the screen?
Yeah, I'm just trying. Give me 1 second. Do you see my screen now?
Yeah, it's coming. Yeah, I can see it.
Okay, perfect. I think I'll just do let me see if I can play some of the sound, because that is what I was trying. Let's see, 1 second.
Yes, it's coming.
Coming, right? Okay, perfect. Good.
So welcome you all to this session. So I also thank Dr. Prashant Kumar Ghosh for accepting our invitation for giving a session in this short-term course. So this session will be chaired by Dr. Rajiv Kumar Jha, who is an associate professor in the Department of Electrical Engineering, IIT Patna. So over to you, Jha sir. Hello, Jha sir, are you there?
Hello, Udit ji.
Yes, yes.
Can you hear me?
Yes, yes, yes. Sir, you can start, sir. Jha sir, you can start.
Yes,
Already welcome.
you are audible.
Yes, Jha sir, can you introduce, sir? Yeah. Your voice is not coming, sir.
Yours is, I am not audible.
I think, sir, you are having issues. So, meanwhile, I can introduce him. Shall I introduce, sir? Jha sir.
Just a minute. Hello.
Yeah. Yes, yes.
Yes,
Now it's
now
coming.
audible. Audible.
Okay. So good afternoon. I would like to. I am Dr. Rajiv Jha, Associate Professor in Electrical Department. I would like to introduce the speaker, Dr. Prashant Kumar Ghosh. Professor Ghosh received his PhD in Electrical Engineering from University of Southern California, Los Angeles, USA in 2011. Prior to that, he obtained his MSc in Electrical Communication Engineering from IIC Bangalore and BE in Electronics from Jadavpur University, Kolkata in 2006 and 2003 respectively. He has been a research intern at Microsoft Research India, Bangalore in the area of audio-visual speaker verification from March to July in 2006. During 2011 and 12, he was with IBM India Research Lab as a researcher. Currently, he is an associate professor in the Department of Electrical Engineering at IIC Bangalore. Before joining as assistant professor, he was a faculty fellow in the Department of Electrical Engineering under the Inspire Faculty Fellowship Program. Dr. Ghosh was awarded the Inspire Faculty Fellowship from Department of Science and Technology, Government of India in 2012. He received the Best MSc Engineering Thesis Award for the year 2006-2007 in the Electrical Science Division at IISc. He was awarded the Center of Excellence in Teaching Award for Excellence in Teaching in the category of Electrical Engineering for the year 2010-11 in USC, University of Southern California. At IISc, he has received Professor Preeti Sankar Teaching Award for Assistant Professor 2017 and Pratiksha Trust Young Investor Award for 2017. He is an associate editor of Computer, Speech and Language, Elsevier. His research interests include nonlinear signal processing method for speech and audio, speech production and its relation to speech perception, silent speech processing, and automatic speech recognition with application in education and healthcare. I would like to invite Professor Prashant Kumar Ghosh to start his talk, and the title of his talk is Dysarthric Speech Processing. Thank you, Dr. Prashant.
Thank you very much, Professor Jha. Thanks for the invite, Udit, and welcome all of you. Good morning. Welcome to this, talk. As you see, the title I'm going to talk about is on dysarthria and dysarthric speech processing. So before I go forward, I just want to introduce. Professor Jha did a great summary of. Thank you for that kind introduction. I'd like to just tell you about the current research group that we are working, where we are as one of the research thread, we are working in the area of dysarthric speech processing. The group that I head is called Spiralab in the fantastic campus of IISc. So a couple of slides on the lab. So this is the a quick view of the lab webpage. Essentially, all our activities are captured here pretty much. You see that we have a pretty vibrant, enthusiastic and energetic team of researchers, students, interns, who actually drive this entire research. And this is a picture you see before COVID, right? We could meet and take such a picture for a long time, and we used to do that soon. So among the various research activities that happen in Spiralab, as you see here, mostly they are centered around signals that are human-centric, starting from speech, and also non-speech sounds such as snore, cough, wheeze, chest sound, lung sounds, heart sound, and so on and so forth. And as you see on the bottom left, there is one research direction that we pursue is on speech pathology, which closely overlaps with the dysarthric speech processing that I'm going to talk today. If you have any questions, please feel free to visit, just Google Spiralab, IISc, you'll get there, or you have any question or suggestion, please drop an email to this email ID. With that, let me now move to the main topic of this talk. So, that we all know most likely signal processing and also speech processing. But dysarthria or dysarthric speech is something that is not very well known. And that is, as you'll see at the end of my talk today, how important this is becoming now, and in coming few years, it will become even more important. So we should really pay attention to this. So let me spend some time now on explaining what is dysarthria. So here is certainly, some kind of presentation plan that I'm going to go through. So it has three main components. One is the I'm talking about dysarthric speech, right? What is dysarthria? And I'll talk about specific two causes of that, and what are the kind of speech characteristics you get. I will talk about those in a lot more detail. I'll give you an idea about the overview of the dysarthric speech processing, which I call DISP, right? Not DSP. This is DYSP. And you'll see the kind of and the kind and types of varieties of research problems, both research and development, that are needed in this area. And then in the third part, I'll talk about a set of experiments essentially that we have been carrying out over the last few years to tell you what we have found out about this dysarthric speech, and to what extent we have been able to make progress. There are very few groups in India who work in dysarthric speech processing, and this is for India. In fact, this is a very, very important problem, as you'll see soon. So let's start with what is dysarthria, right? So let me just play this video. This video is going to show you the anatomy that is involved in speech production. I mean, all of you know, probably we speak through our mouth, right? We use tongue, lips, jaw, velum, pharyngeal wall, palate, teeth, lips, all of that, right? But these are also under, they're being controlled by some muscles, and there are nearly 80 to 100 of them. And these all muscles are being controlled finally by the brain. So this video is going to show you specific muscles that are involved for specific parts of this entire system that produces speech. So for example, for specific muscle names that you see, like the genioglossus, hyoglossus, and so on and so forth, that are involved for the tongue movement. Right? Tongue is a very flexible organ, but to make the right movement for creating right kind of sound, like ta, sa, sha, right? All of these, it requires very fine coordination of these muscles to create such sound. And all of these muscles are controlled primarily by the motor cortex. And of course, this motor cortex talks to other parts of the brain, which controls language and others, right? Which together works to speak certain sounds, certain sequence of sounds or words or sentences, right? So it's a very complex process, and yeah, it's more like an orchestrated process. So anything goes wrong in this process can cause, disorder in your speech or in somebody's speech. So any neurological damage, for example, right, will make it difficult for somebody to move any of these organs or any of these articulators, we call it particularly, either tongue or jaw or lips, right? And once that happens, these muscles become weak, or because of the neurological condition, the muscles are not anymore active. It causes a damage, final disorder in the speech, and that's called dysarthria. I hope things are clear, right? That dysarthria is nothing but a condition in which the muscles which are driving the articulators required for speaking are weak, and as a consequence, the speech becomes disordered. Right? So that's dysarthria. Please feel free to stop me and ask questions if you have. So this is the summary, right? So what it essentially means for an individual is the following, right? He'll find or she'll find himself or herself hard to speak, right? And when you have difficulty in speaking, people will have difficulty in understanding you, and you will have a tremendous amount of social gap. You can't talk to people anymore, and you'll be almost socially isolated, and that's the pathetic condition of some of these patients. I'll just play two examples of a dysarthric speech. I hope you'll be able to hear. Udit said we can hear. Now I'll just try. So I don't really recall what language it is. Most likely it's Kannada. One of the severely, dysarthric patient is trying to speak something which you don't get, right? I'm sure, even if you know Kannada or if you know Hindi, I'm sure you'll not get this if it's in Hindi. This is another sample. Right? So you see, this person is almost like gasping for breath while speaking and not being able to articulate correctly. So different people have different kinds of problems. But essentially at the end, it's a situation where they can't communicate what they want. I'll come to know more about this, why it happens and what are the challenges. Okay. So, sorry. Okay. So now, what are the signs of dysarthria? So first of all, one having dysarthria will have slurred or mumbled speech. That is very difficult to understand, right? You just saw. They'll speak slowly. They can move their articulators as fast as a healthy person. Or they'll be uncontrolled. They'll be too fast. Like the second example was like that, right? And they will be speaking mostly softly. They can't speak loud. They'll be having tough time moving their articulators, as I just said. So the speech will become robotic or choppy. You'll not see naturalness. So once you have all of these, even it affects your muscles that controls your breathing. So you'll have hoarseness in your voice because you can't control your breathing correctly. You'll not be able to control your voice box. So many such things will happen, and then most of the time your sound will come out of your nose because you won't have control on the velum because there's a muscle needed to pull the velum up so that air doesn't leak through that, right? And you'll not be able to, I mean, one with dysarthria won't be able to have that. So they'll be leaking, so it will be nasalized now. So there are all these kinds of symptoms that come out. And in fact, I must tell you some of the experience that I have myself while working with these patients. You know, we have patients, these particular patients, right? They typically, you know, will have almost paralysis, right? Because they can't move things. In fact, that's not just going to happen on their vocal system, but also the entire body, because they're all muscles, and all muscles will become weak. But dysarthria is specifically, you know, the vocal part of it. But any disease which will cause this will also cause other muscles to be weak and inactive, and you'll be paralyzed. And many times what happens, these patients, very, you know, very pathetically, I'll say, they die because of choking. So at some point, they even can't swallow their own saliva because their muscles are so weak. So the saliva goes into the lungs and they die, right? So this is some of the bad endings. So we had patients whom we were recording and they died in the process of recording, meaning, you know, we recorded once and recorded second time, and third time we call, is no more, in matter of, you know, a year or year and a half, right? So I'm going to talk about all of those also, but we'll be curious, what are the diseases that causes this, right? So typically it happens because of stroke, where it damages the brain, right? Or any other brain injury, or tumors, or can happen Parkinson's disease, right? Or amyotrophic lateral sclerosis, or Huntington disease, or multiple sclerosis, cerebral palsy, many such, right? And covering all of these, I mean, each of them have their own intrinsic way of damaging the vocal system. And I'm not going to talk about all of them because that's too much. In fact, we are not also working with all of them. In particular, working with two of those. One is Parkinson's disease, which I'm sure many of you have heard, and the other one is called amyotrophic lateral sclerosis, ALS. And probably you haven't heard that much, but this is even more devastating disease. I'll talk about that. So let me now tell you about ALS first. What is ALS? So this is also known as, by the way, MND, motor neuron disease, or Lou Gehrig disease. This is the name of the player, the American football player who first had this disease, or at least diagnosed with this disease long back. And this was the disease was named in his name. And this motor neuron disorder happens because the connecting neurons from the brain to the muscles, right? Each muscle is connected to the neuron to the brain through a sequence of neurons, and these neurons die. So the brain is active and working fine. Muscle is active, having its nutrition, but the connection from the brain to the muscle gets damaged. So even though brain creates signals, muscle doesn't receive it, and it weakens. I mean, once the muscle, the neurons start dying. In fact, even one neuron dies, you can imagine what will happen, right? Maybe one or two, you can still communicate because there are multiple communication channels, but with time, quickly, many more neurons die and your muscles become just not controllable anymore, right? And because this is a degeneration and you lose control of the muscle and you fail to speak. And this is true not just with your muscle involved in speaking, but any other muscles. So what are the symptoms? As specific to ALS, I mean, those symptoms that I talked about are in generic, right, for dysarthria, but ALS, you can have muscle stiffness, hard time in holding items, muscle cramps, swallowing problem, as I just mentioned, right, speech difficulties. I'll just play 3 samples of dysarthric patients with ALS, and you'll see these 3 are from 3 severity levels, right? One is extremely severe, another is not. So you'll see the differences. Let me play that. These are recording all in Indian languages. Right? You got that? Sorry. Oops. So you got that, right? So from the left to right, it was getting more severe. So as you saw in the rightmost audio file, you couldn't almost understand, but it was looking, at least the leftmost one was sort of natural, or maybe from a healthy person. But there is also disorder there. Coming to the Parkinson's disease, it happens for a quite different reason. Not that the channel bit for the connecting wire, the neuronal wire, if I call it, that gets damaged. So that remains okay, but the brain gets damaged. the part of the brain which controls these muscles, they get damaged. So this is again a progressive brain disorder, like dementia, right? Where the nerve cells which are involved for muscle control, they die, and this happens primarily because of the neurons that lack of those neurons or death of the neurons which produce dopamine, right? So once dopamine level goes down, the brain fails to handle the muscle movements, or the control the muscles required for movements. Again, similar kind of symptoms, slowness in moving, speaking difficulties, difficulty swallowing, and all of that. So let me again play 3 samples. So I hope you got the sort of an idea now what is the kind of speaking characteristics that they have, and the okay. So let me now tell you about how widespread are these diseases. So the ALS, it happens, nearly in India at least 1 in 100,000 people, and worldwide it's nearly 2 in 100,000 people. And for the case of PD, it happens, 7 to 10 million people are affected at any point of time, right? So it is not as much as, for example, asthma, right, or COPD, or not other heart, any other disease that causes life-threatening. But this is certainly life-threatening, but it doesn't happen that much. But the growth of this disease has become really concerning these days. And more concerning is their life expectancy. So once somebody is affected with ALS, they die. 50% of them will die in 3 or a little more than 3 years. 20% will die 5 or more than 5 years, and remaining 10%. So very few people actually live longer. In fact, living with ALS is disastrous. Life just becomes miserable, right? And again, for PD, as you see, it has now increased because of several kinds of medical interventions and many other technologies that have come up. It has increased from 9 or 10 years to now 14 to 15 years from the point of from a time of diagnosis. Right? So how does the diagnosis happen? In fact, there is no specific test. Like, you can tell somebody has a blood sugar if you test sugar in the blood, right? But here there is no such test. And often what happens from the doctors, as I've talked to them, right? We work closely with NIMHANS here in Bangalore. They say that it's very difficult for a general doctor, unless they're experienced with neurological diseases. They treat it as some other problem. For example, many times the patients that come from far, they say that they went to some local doctor and they thought that it's their problem with their teeth because they can't speak. So they remove all their teeth, but still doesn't help. So they finally come to this doctor and they do neurological examination, history, medical history, right? And together all of that and the experience and some questionnaire, together they decide that you have ALS and PD. And the doctor, Dr. Nalini, that we work with, and many other at NIMHANS, she says that telling this to a patient is just killing them on spot. And she keeps on doing that every day. Every day, 2 or 3 patients, she has to tell that you got this, and your life will be no more. You'll not be there anymore after 3 years, and it's just devastating, right, for the patients. So people are getting more and more aware of this disease, and you may have seen all of this that I'm showing on the screen. Various kinds of initiative, awareness that are happening, starting from Ice Bucket Challenge to creating technologies that can help them walk, write, draw, paint, any such. I mean, it's just becoming more and more prominent these days, and we hear a lot more. In fact, I'd like to show you this particular one. I was watching, you may know about Paralympics, right? India got a lot of medals there. And the closing ceremony, if you watch of this Paralympics, there was a, I think, final clip that was played. And that was composed by Pone, is a French musician, or producer, right? He is now down. He is down for several years now with ALS. He can't speak, he can't move. He's eating and everything is just like he has to be fed all the time. But his eyes are intact. In fact, what I hear from the doctors is that the kidney, the eyes, and your breathing, that still remains till the end. You can still blink your eyes, although there are some, but these are voluntary muscles, I believe, right? So they are not affected, luckily. So this particular, producer have been producing music using his eye blinks. So he has a very, you can go and search his name. You'll see, it requires a completely different setup just for him to work like that. So you may be wondering, well, then once we have somebody has ALS or Parkinson's and go to a doctor, how the doctor tells at what stage of the disease you are in, right? You're already just beginning or you are severe, right? If it is ALS, then if you are detected early or late, you can't stop it. Whatever way you try, it just progresses. If it is PD, if you are Parkinson's, if you are detected early enough, then there is still some hope. With some practice, therapy, and others, you can still go a little bit, because some part of the brain has got damaged. But in ALS, the entire pathway is dying, right? Also, the brain is intact, so it just goes so fast. And in fact, people I've seen young people like 24, 25 have been affected by that, right? So it's very, very sad. So what rating scale doctors use for quantifying or telling at what stage of the disease you are? So there are two, one for each of these diseases. For ALS, it's called ALS Functional Rating Scale, revised, R for revised, and the PD is called the MDS UPDRS. I'm going to describe each of them in a brief. And this, the speech is one of the components through which the severity is determined. So if you want to know more about ALS FRSR, this is a very good paper, and that's mostly being followed even today, right? So there are various components in this, nearly a dozen of them. So speech is the very first one, right? As you see, under speech there are 0 to 4. These are the categories, right? So 4 will be the normal speech, 3 is the detectable speech, 2 is intelligible with repeating, 1 is speech combined with non-vocal communication, and 0 is loss of useful speech. So what happens? Doctors make them speak. I'll come to what they make them speak, and then judge based on that. And doctors will also check all the remaining salivation, swallowing, handwriting, cutting food, handling utensils. They'll ask their relatives that it's a questionnaire, how difficult he or she finds. Then dressing, hygiene, turning in bed, walking, climbing stairs, and many more. You see 12 of them. So all these questions, doctor gives score in each of them, and finally you get one combined score. But for our engineering dysarthria purpose, right, we'll be sticking to the speech part of it. For the Parkinson's, it is from the Movement Disorder Society, MDS, and this is called the Unified Parkinson's Disease Rating Scale, UPDRS. And it's just, this PDF is freely available, but if you'd like to use, you have to take that permission for that. Even here, there is a large number of questionnaire, a large number of, list of questions that we go through. So there are 4 main parts, starting with non-motor aspect of experiences in daily living, right? And it has 13 different questions, starting from cognitive impairment, hallucination, depressed mood, and so on, right? Next is part 2 is the motor aspect. So one of them will be speech, as I just told you, right? Speech involves a lot of motor functions, muscles involved in moving your articulations, and saliva, drooling, chewing, swallowing, all of that, which are involved in. Then, in particularly, I just want to highlight the speech part, right? As you see, this again goes from 0 to 4, but it's just the opposite, right? 0 is normal, 4 is severe. So no problem for 0, but 1 is a slight problem, 2 is a mild problem, 3 is moderate problem, and 4 is severe, where the entire speech is not understood. Then in part 3, there's motor examination, right? Again, speech is one of the component. Even there, they bring the same set of, a slightly different set of questions, but what you hear from the patient is different. I'll come to those details in a minute. And then finally, in part 4 is motor complications. So there are various specific tasks they ask them to do, right? In terms of their movement of the fingers or specific kind of sounds that they ask to produce, and then they check whether there is any motor complications. So based on all of these, they give or judge the level of severity of disease. So I hope with that you get an overall picture now what happens from the point of, and this is how they diagnose, right? In some sense, there is no specific way. And then the journey begins for these patients where they have to go through this very tough time till they are normal. So for all these kind of interventions and treatment, we will be wondering what kind of speech task. There will be other motor tasks the doctor asks them to do, but for speech pathologists, they go for some specific speech tasks that are clinically useful, and this comes primarily from the understanding of the perceptual features. So let me give you some example, right? So what you see on the columns and rows, on each row, you see the type of dysarthria. There are various kinds of dysarthria, and they are defined based on what you see on the columns. Meaning, let's say the simplest one, let's say hyperkinetic, let's say, right? You see my cursor there. So it has, let's say, articulation inaccuracy, as you see here, and prosodic abnormalities. It means that when I ask somebody to control their prosody, meaning pitch, right? Suppose I say somebody, let's say la 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 la, right? You have to have a certain control of articulation and the pitch, right? La la la. So it's a coordination between the two, and they have very poor. So that's called hyperkinetic type of dysarthria, right? When they have this kind of components, and so specific speech tasks cater to specific kind of features, as you see on the columns. If you are more interested to know, you can read this paper. It's a very nice, survey of dysarthria in ALS by Tomic. As you see, depending on the kind of dysarthria, different parts of the motor neuron or different areas of the motor neuron gets damaged, the lower or upper. And you see, depending on which part of the neuron gets damaged, according to that part of body will be affected, right? For upper motor neuron, you'll have the poor tongue movement, right? And various others. I'm not going to go through those. If you're interested, please spend time on learning them. So now with that, what doctors have come up with are primarily 3 types of speech tasks. The first one understands or checks your respiratory phonatory coordination, meaning you ask the patient to speak sustained sounds or vowels, for example, ah, for as long as you can, so that you check how much they can hold their breath and speak. Like as you saw in some cases, right? They're gasping, right? They're out of breath already. So that this can be checked. And when you say ah, in fact, when you phonate, if your muscles are good, you'll be holding that like ah, like that. Otherwise, it will become ah, right? Similarly, you have diadochokinesis testing, where they ask to speak certain syllables like pa or ta or ka, and repeat it as fast as possible. So for example, they are asked to speak like pa 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 pa, right? And I'll play you some samples we have recorded, and you see how they changes compared to healthy. Similarly, it's ta 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 or ka 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 or pataka pataka pataka. Right? So that's called diadochokinesis. It checks how fast repeated speaking you can make. It requires very good control of your tongue or lips and at a good rate. Next is the speech characteristics. It can involve them speaking, reading a sentence, and or speaking out naturally, right? It could be either of those. And what it captures is essentially their articulatory precision, or prosodic structure, or resonance, voice quality, intelligibility, and many others. So it's all combined into this. So I just at this point want to show one example of the diadochokinesis task from these 3 categories, meaning one is the ALS, amyotrophic lateral sclerosis, Parkinson's disease, and healthy control. Right? So as you see, we are plotting for 1 second, right? Although I'll play the clip for a longer time, but you see that in 1 second, the ALS person could hardly speak just one time. Pa. PD tried, but you see there is lack of coordination. Sometimes there's a less gap, more gap, right? But healthy control, of course, does it much better job. Let me play and see if you can hear that. right? You understood that he's struggling to speak, essentially. He's a very severe patient. He is not saying to speak pa, he's saying ma, because he can't touch his, his velum is down, so all sounds are coming through the nose. Then Parkinson's. Like you're feeling like he's gasping for breath. Then you hear the healthy people. You can clearly see the difference, right? So they have this lack of control on their muscles. So that I covered the first phase. Any question I'll be happy to take at this point if you have. Otherwise, I'll move to the next phase.
Yeah, I have one question.
Please.
Yeah, how?
Sorry, I can't hear you. Hello? I can't hear you. Hello? Can you? Can others hear me? Hello?
Yes, yes, your voice is fine.
Okay.
I think he's having some issue with mic.
Hello.
Yes,
Yes.
now it's coming.
Right.
My question is how nose is related to dysarthria. Nose.
Yeah. So are you saying, if I understand the question correctly, are you saying how nose is related, right?
Yeah.
Yeah. So you see, when we speak, the air comes out, or the sound comes out both through nose and mouth. And the way we control is through what is called velum. So there is from the palate, there is a very soft part that hangs, which, with your muscle control, you can push it up and it touches the pharyngeal wall so that the air doesn't go through the nose and only comes through mouth. For example, if I say ah versus ma, right? When I say ma, I'm forcing the air to come out because I open the nasal passage and sound come out. So these patients who has dysarthria has weak muscle control, they find it difficult to control that velum, meaning lift up. So velum will be always in a falling down state. So air will come out. So most of their sound will become nasalized.
Okay. So actually, my basic question is there are different parts in the mouth, from mouth to brain, and this particular problem is associated with different parts of the different parts of these regions from mouth to head. So how can you distinguish that which signals are basically associated or which signals are basically responsible for this particular problem? And because their nature of signals will be totally different.
Correct. Good question. Very good question. See, that is why I will show you the example, right? The speech task that's carefully designed. So when I say pa ta ka, if you carefully observe, the pa is a labial constriction, meaning you have to have control of your lips to make pa sound. If it is ta, it means you need to have a control of your tongue. The tongue goes and hits for ta, right? For ka, it's the back part of the tongue, which is called velar constriction. And also there are sounds like ma, na, right? You can ask all of this. So by using various sounds, they capture this various aspect of the articulation and which part has gone more wrong than the others. So we give this target set of sounds, words or phrases, and even if you speak naturally, right, you will be able to figure out because their target sound will be some, and they'll be won't be able to achieve that in some sounds, but for some they'll be able to achieve. I hope that answers the question.
Okay, so my normal question is, so did you get data sets related to different parts of the sound?
Yes, I'm coming there. I'm coming.
Okay, please.
So now let's move on. I'll just give you now an overview of the disc, right? What is happening? I mean, it's not that we are working in all aspects, but these are happening all over the world. So let's see. Yeah. So just to capture all of that, in one slide, actually this may not have captured everything. There are many others, right? I'll start from the very right top, which is this quality of life, right? There is a lot of research on quantifying the quality QOL of these patients. In particular, they figure out what aspect in speech are most contributing to their quality of life. For example, if we suppose, think of this way, right? If we can speak 5 vowels correctly, even in dysarthria, like a, e, u, right? In fact, it has been shown it is not the case. Actually, the vowel triangle collapse, meaning all vowels become similar. So they quantify with what sounds you can actually maintain still your life. Meaning, let's say you want, essentially you are paralyzed, you're lying down, you just want to communicate, I want water, or I want to go to restroom, or I want food, like 5-6 different items. If you could have spoken those sounds, you could have probably maintained your life. You have, of course, a caretaker, but the unfortunate part is, what doctors say, the mosquito is biting and you can't hit it, neither you can tell somebody to hit it because you can't explain that some mosquito is biting, right? So they're saying that if you can figure out and train them to say, okay, these are the sounds you have, and and you can speak well, and that is again individualized and also disease specific. That will be great. So I'll just tell about each of these through one slide. I'm not going to go into much detail because I wanted to talk something that we are working. I'm sure you'll be interested to know the real data and what we have done from there. Then the next one is called augmentative and alternative communication, AAC. As I said, their eye blinks are fine till their death, right? The composer I just showed you. So can you develop technologies with their eye blinks? They can do everything that they want. Next is automatic dysarthric speech recognition, right? We have enough solution for normal, healthy people's speech recognition, but not much for dysarthric speech because of low resource data. I'll show you some, example references. You'll see how people are tackling that. Then acoustic analysis of dysarthric speech. And there are plenty of questions that we need to understand about. And people have done, many things are left. Some of them we are trying to work out also, right? There are enormous research questions there. Then there is articulatory kinematic analysis, where we actually record their motion of the lips and tongues. And with that's what also we do with these patients. Then early detection and monitoring. You want to, even before they get this disease, right? So it's not that one fine day you suddenly have this disease. Essentially, this speech distortion starts happening slowly, right? As I said, the neuron dies slowly. Not one day all neurons die. And similarly for Parkinson's, the brain doesn't just give up one day slowly. Can you detect that early and raise a flag that you see in your speech, we see something happening? Go and check this doctor. Things like that. So I'll just tell one slide summary for each. For quality of life, as I just said, the question is, is there a common pattern that these dysarthric patients have from various diseases have common that we can find out that interferes with their quality of life? Or is there something that some speech parameter or dysarthric speech parameter that can correlate well with their quality of life, okay? And so on and so forth. So I just try to keep one reference, but that doesn't mean just only one work have been done in the past. There's enormous work, amount of literature done on the quality of life. But I must say I have seen through my experience there are less from engineering angle, and I think we have a lot of potential, chance or of contributing for that, being an engineer and actually signal processing machine learning people. The other one is AAC, augmentative and alternative communication. Use eye tracking, brain-computer interface, voice message banking, personalized TTS. In one of the paper you see down there, they're actually trying to develop a personalized TTS, right? You imagine and it speaks, or you blink your eyes and it speaks, things like that. Then about automatic dysarthric speech recognition, there are plenty of work. In fact, there is a group at TCS who are working in TCS Mumbai. I see a few papers from them. This is a paper from Google, right? They are trying to use the low resource data for dysarthric ASR. Acoustic analysis, there is again plenty of those, right? Starting from how the format changes, how space change, speaking rate, how they change, right? Pause pattern, and you have some interesting findings there as well. Prosodic analysis, how do you detect even a person, even a normal person apparently may have dysarthric speech somewhere as he or she is speaking, right? These all will become enormously useful. And there are a few example references here. Finally, articulatory kinematic analysis. Again, this is all to do with measuring the motion of these tongues and lips, and with some specialized device, which I'm not going to talk about much, but will touch a little, although we are working together with Nimhans. And then figure out that, okay, if healthy person move their tongue at, let's say, 5 times a second, right, pa 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 pa, right, or ta 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 ta, how much the people with dysarthria can. Is it significantly different? And can I correlate that with their severity, right? That will be a good way to quantify that, okay, you can't move your tongue that fast, that means this is your severity. Or you move 1 time a second, your severity is 0, things like that. Right? And then early detection and monitoring is of great value, and that is one of our project that we are working with Nimhans, supported by DST again. Discover speech cues for early detection and tracking some of the speech parameters for monitoring dysarthria. Right? So with that, I'll quickly close that because we can actually talk much about each of these, but I wanted to talk something specific that you. So with that, I'll move to the third part, where I'll just give a summary of experiments and findings, and you'll see how, to some extent, we have found some characteristics that can be used to develop some of these technologies for assisting these people. So this all that I'm going to present now is with collaboration with Nimhans, Bangalore. Dr. Yamini is a speech pathologist. Dr. Nalini is a neurologist, and Dr. Ravi Yadav, again, neurologist. We work with them, and the patients are recruited by the neurologist, and then the pathologist check them, and then we record. And just to give you an idea how we have done the recording setup, and these are, again, we had to unfortunately stop all this because of COVID for last 1.5 years. But before that, this was how we are recording. So we have this kind of recording setup, as you see, right? You have the laptop in the front of the person. So the person will sit in the chair here, and there is a high quality Zoom microphone. Laptop also will record something. And then there are 3 smartphones. And there is 3 price range. One is Xiaomi, and there is Motorola, and there is Apple iPhone. And then, as I said, laptop and a professional recorder. Why you are recording all of this? See, think of the long way, that the way you are thinking, right? Any technology that you develop, nobody will use a high quality microphone and speak there, right? It will be their phone only at the end, the smartphone. If you develop anything, they have to use it. So to make sure that anything that you develop work in these multiple devices. And of course, in variety of recording condition as well. Some of those also we are addressing as we go through the research question. So these are recording setup. Some of the examples, as you see from side view, so he's the patient, right? And he's the experimenter from Spire Lab, and what he does, he controls what comes on the screen. Now, you see, I must tell you something that we learned in the very beginning of this project, which is like nearly 3 years back. A patient comes from some rural part of Karnataka or Bengal or Telugu, right? Andhra Pradesh, right? Or Maharashtra, somewhere, right? They many times are illiterate. So they can't read. So if you even show them a sentence to read, they can't read the sentence. And we had a tough time in figuring out how to record them there. So what we have done is we present images on the screen and let them speak about that image. And that those images are very either funny or from their daily life. Okay, so that they at least get engaged by looking at, by saying, they can say something about it. Okay, so now the experimenter controls that, and he speaks, and everything gets recorded. So we have parallel recording from all these devices, right? Now I want to just show you on a, to give you a lighter feeling here. So this is one of the images we use, right? And we have nearly some 150 to 200 images that are chosen not to really, I'll say, bore them, not to really, and this is something very, very, it's psychological. I'll tell you some experience that I have personally, because I used to go and record even with the articulated data, because we do work with electromagnetic articulograph here to capture this motion of the tongues and lips. So let's say I attach the sensors on their tongue, right, and we ask them to speak. So when you give them some specific task like this, for three kinds of speech tasks, as I told you earlier, I'll just describe you now. But once, you tell them, speak something that you want to speak. What happens with all of these patients? Suppose you tell them, they can't figure out what they speak, but if you tell them, just tell, okay, can you tell the last birthday celebration of your grandchildren? They start there, but slowly they come, in a minute, they come and fall back on the disease and start crying. And it becomes so difficult to control them at that point with all the sensors attached, microphone around. So recording them is just a different experience. I must. So doing research here, actually dealing with people of real nature, right? So I just want to tell you that to understand the challenges. So we show these images. They are like, you'll see some of the recordings out there. They'll be laughing at some part. Ek hathi scooter chala raha hai, right? Something like that. They'll speak, and they enjoy it. At least they are different. Okay. So these are small things, but these actually matter in doing the experiments. So we have this 4 speech task. I wanted to tell you that there are the last task, which was speech. We broke it down into 2. One is picture descriptive task and spontaneous speech. And then you have the diadochokinesis and sustained function. Right? We are recording all this 4. I'll just show you some examples. So this is picture description task. Let me see if I can. Now you understand, we have no idea what he's speaking, but he's trying to explain that. But a lesser severe patient. So he sort of got that, right? The Parkinson's disease. Okay. And the healthy. Okay, you see the difference, right? And like that for all others. I mean, I'll be happy to play, and if you're interested, I'll be happy to. So all of this, each of this speech has their own nitty-gritties, and each of the speech tasks. And you'll see we have done experiments with all of those, and it'll be some interesting. So let me just show you this pataka. It will reveal. Right, we already saw that. Oops, sorry. Another one. Parkinson. Healthy. Right. So and then similarly sustained function and so on, so forth, right? So this gives you an idea as to what we did in trying out the recording, and we have been recording for quite a few years. So we have collected good amount of data to really train such models. With that, what I'm going to do is probably I'll just lay out. Allow me to go back to the slide of the content so that I can tell you at least how I'm going to present these research experiment, right? So I just covered the first bullet, collaboration with enhance, right? How we are collecting the recording. Now, the way I'm going to present this research, so far we have done the experiments, is the following. So first we'll show you that we have found out some standard acoustic features and some articulatory features. By that I mean these are from the recordings, which I have not shown the images of, where we actually put this person in an electromagnetic articulograph machine and record his motion of his tongues and lips. And we have very little data on that, by the way. Very difficult to put such a patient in that device. And then I'll show you, and we did experiment, and I'll show you the findings and how this performance in terms of the classification of a healthy person versus an ALS, or healthy person versus a Parkinson's disease person or patient changes depending on what device you used or what speech task you used, right? If we can quantify that, and this is something that was not done before very systematically, it will tell us which task to use in practice, right? If we find out that, okay, let's say diadochokinesis is the task which reveals or is most accurate in classifying, then we better use that task without bothering the patient too much with any other task, right? Even if you can think of building some application, you should actually use that task. Then we'll show you that we went further and built complex models using deep learning for this classification, right? Then we said, well, instead of using some knowledge-driven feature, can we learn features? And we have some interesting finding even there, you'll see, for this ALS PD healthy classification, when we learn some features using neural networks. Then you can build complex networks and they'll do really well in lab condition recording and so on and so forth. But you can't really deploy such complex model live on a phone. You need to have a lightweight model, accurate enough in noisy conditions. So we also do some experiment in that regard. That's about model complexity and noise robustness. And then in that, when we did that experiment, we found out very interestingly that there are some source features and not vocal tract features. They are very robust to noise and very accurate as well. So we just published this in last interspeech, where we showed how source and vocal tract features compare with each other for such classification tasks. And we are constantly working on many other problems, including enhancement of this quality of this speech. That is one part of the acoustic analysis. We are working on predicting the severity of the patient, because that's going to be useful for tracking and all of that, right? So with the work so far, we have actually developed an app called Neuro Companion that was part of the DST project. You can find it in Google App Store, where we have deployed some of these models and where you can speak, and it gives you a score between 0 to 1 to say where you stand in terms of your healthy to fully deserting speech scale. So with that, I'll just start and I'll take you to this set of experiments, and that will give you some idea of what findings we have. Okay, so let me go back. So the first question we're asking is this, and this is the paper in 2018 that you have. So what are the acoustic and articulatory features that are good for classifying given one recording or whatever speech task into the healthy versus dysarthric speech? And this was done with only ALS. So as you understood, as you kept on recording, the number of subjects kept increasing as you see the later experiments. And initial experiments will have less number of subjects. And also you'll see that the disease, because here we are done with ALS because we didn't have enough PD data then, and so on and so forth, right? So as you see, I'll show you more experiments, the amount and the nature of data will keep becoming richer. So here for this particular experiment, we used 3 different speech tasks. One was repetition, and these are recordings that are done with the articulatory device called electromagnetic articulograph, which was recording the motion of the different articulators. So the first task was a sentence like this, that my name is blah 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 and I'm now in Bangalore, in their native. There's no English here, everything is Indian language, and that's unique about this corpus, because having English will help you to do something with existing databases, but here we are completely weak in that sense, because we have to build our corpus. Okay, so now that's the first task. Second task is they'll make a monologue, right? So it's a spontaneous speech. And third task was that they repeat some specific Kannada words, and they're all Kannada speakers. So words like Topi, Karnataka, Pustaka, Pain, Alilu, and many others. Right? So these are 3 tasks. And we have very little set of subjects, healthy people, 8 of them, patients, 8 of them. And as you can see, the ALS-FRS score are in the sort of mid-range, 2 to 3. And age we try to match mostly to the extent possible. And you understand that, right? Even if you try to, and you can see the gender not fully balanced. Even if you try to balance, you can't, because you can't recruit them. And you have to wait for them to come. In the hospital, has to wait for a female patient to come so that we can get data from. And you must, I must tell you that you should appreciate as well that when you get a patient, it's very difficult to get recording from them, because they think that they have come here just for getting the treatment done. Unless you really motivate them, it's just difficult. In fact, we are trying now to do remote recording, contacting them every day, just doesn't work. So they don't see value of any of this. So doing this research is really difficult. It's not healthy people that you can bring and speak and pay them. They don't care about payment also, right? But they just want their problem to be solved, not to speak and realize that it not help at the end, right? But I tell them that we are working for, if not them, but their coming years. But who cares about those? So here is a view of the sensor that we place, right? We place 3 sensors on the tongue, 2 on the lips or on the jaw. And we place this subject on a machine called EMA AG501. I'll not go to, because of time, I'll not go to the details of that, but that's another interesting. But you can always visit our lab page to know what is this device. We have this device at the lab, but we do the recording at the hospital, right? So essentially, we collect the motion of each of the sensors. You can think of that, right? XYZ coordinates. So overall, we had a very little data, I'll say, in this case, because we had rehearsed speech. Typically, from a patient will come in the range of 6 seconds to 19 seconds. Similarly, for spontaneous speech and repeated words, you can see these are per patient, by the way, right? How much data we get. Then we came up with a few of these features. These are some of the articulatory features. So we have 6 sensors and 12-dimensional articulatory feature. We just take X and Z, meaning we don't take motion in this direction because we typically don't move our tongue in this direction, which is perpendicular to the mid-sagittal plane, right? So you always take all the motion in this mid-sagittal plane and take those values and create these velocity and acceleration features. And we found them to be very useful. You'll see them soon. So we have this velocity feature, 6-dimensional, acceleration feature, 6-dimensional, then together, right, 12-dimensional. Then there is some, we compute the static velocity and acceleration together, and we get another bigger feature vector. Then FCC, of course, is standard and all features. So just wanted to compare this kind of various articulatory features and the acoustics features on this small set for the classification of the ALS and 2DP. And this is how I did the classification, 4 cross validation to make sure we systematically do things. And we take the suprasegmental feature, meaning whatever feature you have, take it over 8 seconds and compute mean and standard deviation. That tells how much variation you have in those features. So the classifiers are SVM and DNN, and the suprasegmental features are used as the feature vector for those classifications. And for a recording, you have multiple segments of 0.8 seconds with a shift of 0.2. For each of those 0.8 second segment, you will get a decision. And you combine your majority voting and declare this utterance to be healthy or ALS. So it's a simple, sweet experiment, right? A small set of data. Let us see what is the result we get. So if we use the SVM classifier or DNN, you see, first of all, the numbers are on the higher side. You can see that. That's one thing. But what is more interesting is that the articulatory features in general, the numbers, are better than the MFCC features, meaning acoustic features. MFCC are standard features, I'm sure many of you know. When it gave better numbers with the articulatory features, it simply tells that probing or figuring out articulatory motion, if you can somehow figure out articulatory motion, that are more direct indicative of this disease condition or rather this disease. So we are working now to a great extent to quantify that, right? We do work with a lot of technique that does acoustic to articulatory inversion, meaning from speech can we go to those articulatory spaces that may help us to decipher some of those characteristics of the articulators. But here is a direct measurement. So that's revealing. And even you can see there are a few cases, for example, depending on this task also, speech task, right? You see that, this task, speech task 1 was giving very 100% accuracy, in fact, for all the folds, right? This is standard deviation in the bracket. For all the folds, that was amazing, which was not the case with the DNN. In fact, SVM was more discrete. But these are again numbers. There is no great sanctity about choosing one number and claiming big things about it. These are just relative to understand, compare with MFCC on the same set. So articulatory features are more informative than acoustic features. That's all. And in fact, when you talk to the doctors, they also say that when the patients speak to them, they just don't listen. In fact, they say that when they talk to the patient over phone, they have much less understanding about their condition than face-to-face because they can see moving their lips, tongues, and all, and they can easily get. In fact, one of the prominent symbol or symptom, I'll say, in the articulation, I have seen that myself many times with these patients that have recorded, their tongue will rest on the jaw. So for example, this is a jaw, right? So your tongue never goes up like that. So it is always on the jaw. So if they say ta, they don't do ta, like tongue goes. Their tongue is resting on the jaw. They'll say ta, ta, ta. It's just classic. You just get to know that. If you just hear over the phone, you won't get that. Right? So these are very obvious articulatory features that you can tell these people have this disease. But well, now the next question comes, right? As you're recording more, does it matter what device you're using for recording? I'll just quickly show you, not go into the details now. We have got, bit more subjects, at 50 subjects now with 5-fold cross validation. And we have recorded, as I said, all the recording devices, 3 kinds of speech task, right? And from all kinds of language now, right? We're getting the corpus more and more. And this was in 2019. And the amount of data is also good, right? 7 hours and 5 hours and really 8 hours, right? And what you see here, the columns are these 3 speech tasks, right? Spontaneous, DIDK with the diadokinesis and phonation, sustained phonation. And on the rows are these device name: Motorola, Zoom, Xiaomi, laptop, and iPhone. What is plotted here is the F-score and the accuracy with the chunk size. I think both are F-score. I think these are with two different models, the SVM and DNN. Okay, so with SVM and DNN, you will get the accuracy of by using certain chunk for computing features. And as you see that, so depending on the task, so it's a task and device combination. So let's take DIDK. You see they are typically on the higher side. That has also happened in the previous experiment. So you see typically they are, if you look at for this task, if you compare all the devices, Zoom, which is the highest quality recording, you see this on the top, of course, but Motorola is not that far off from them, right? In fact, Xiaomi, so they're nearly 90% range. But spontaneous is a little lower, and all of them are sort of in the same range. Similarly for phonations. Phonation is the least performing task, or least, it's a task that gives least accuracy. So what gave us belief is that although we are not losing much, but there is some loss, may not be significant enough. So we currently what we do is typically build model with all these recordings, so that the model has all these device recordings. Okay, with that I will go further and then say, we ask the next question. Okay, great. So you did, with sort of small data, you could do a good job of classification between, ALS and healthy. How about ALS healthy? That's okay. Parkinson's disease and healthy. Right? That's also some question. Can I even classify whether it's ALS or Parkinson's disease given a recording? Right? That's also another question. This is what we did in 2020 ICAS. So I'll just give you an idea here. So we use now a complex model using neural network called CNN LSTM. So what we do is we run it through only CNN and do max pooling, and whatever feature comes out, we pass it to the time series modeling through LSTM, then feed it to the dense layer, and then do a classification of either ALS versus PD, HC, healthy control, or PD versus HC, Parkinson's disease versus healthy control. But what is done again is the majority voting. Given an utterance, you have multiple chunks. We take feature, the super segmental feature like this mean standard deviation in each chunk, and those are fed to the fed to the CNN LSTM classifier, and then you take a decision in each chunk and then do a majority voting, and you get the classification out. And that is much more robust when you do a majority voting. And we also do a transfer learning. So with the scenario that you imagine, for example, in some languages we have more ALS patients than Parkinson's disease. So the question is, how do you build a Parkinson's disease classifier with healthy control in that language? So the question we asked is, can you build a ALS versus healthy control first, and then do a transfer learning, right? Do a pre-trained model with that, and then fine tune with the little data of Parkinson's, and vice versa, right? Like that we did experiments. So now, primarily our objective was threefold. First, to see whether this new model, CNN LSTM, does any better than SVM-DNA, so that we can say that we have a better classifier. Number two, for this transfer learning, right, two-class problem, can you show that indeed we do get a benefit? Suppose we have a very little Parkinson's data, we build a model with ALS and show that with this data, whatever we adopt this model, that it does much better than using the small data alone. That will be an interesting finding. And third is, can you do a three-class classification directly with the CNN LSTM? And in fact, we have taken this three-class classifier with all the data and then fine-tuned also with the individual, and that also improves things. I'll just show you some results. But now this time we have much more data, right? Now nearly 180 subjects, right? 60 ALS, 60 PD, and 60 healthy control. We try to make as much balanced as possible, given that we have a lot more data, and you see the data size also. And again, we do systematic evaluation needed for publishing a paper, as you all know, right? 5-fold cross validation, and make sure we, disclose all the details of the models that we use. First, we had three objectives. Let me tell you the first one, right? CNN LSTM, does it do better than SVM CNN? Yes. SVM DNN? Yes, it does better. So essentially, there is information in the temporal dynamics of these features for this ALS HC classification. Then next question came, okay, can we do the transfer learning and get any benefit? So let me One second, let me change my pointer. That may be easy for you to see. Yeah. So look at this. I'll just explain this. So the top row are for the ALS versus healthy classification, and bottom row for the PD versus healthy, the Parkinson's disease versus healthy classification. So what you see here, the columns are spontaneous, DIDK, and phonation task. Okay. Now take any task. So let's say you take the phonation task. Let's say, right? So what you see in the blue curve, the blue one, is the randomly initialized model trained with whatever data is available. So here is 100% of the data, entire data, and we prune the data, meaning just reduce it randomly sample to 10%. Of course, it's going to go down, right? The performance, because we are training with less amount of data, so it will not get trained well. But then what we did is, well, you do a transfer learning. So here it's a ALS versus HC. So we built the treated model with a lot of PD data, and then fine-tune with the little ALS data, which is 10%. And as you see, it does better than just using that 10% of the ALS. In fact, in some cases, this gap is drastic. So these are for PD versus HD, just like that, right? You see that sometimes the gains are very, very good and beneficial. And you can look at the DIDK, which is so far we have found to be the robust task. You see the benefits are really enormous, right? With the 10% of the data, you get enormous benefit for PD versus healthy classifier. And you get some benefit again for the ALS versus healthy classifier. I hope that makes a point, right? So it shows that if you have low resource condition, you can use the other kind of desert speech, pre-trained and fine-tuned. Let me move on. We also did this 3-class classifier building with CNN and LSTM, and then use that as it is for ALS versus HC or PD versus HC, and they gave this kind of numbers. But when you fine-tune them, it does better. In fact, that is the best performing classifier. So all these are now, you see, we are moving towards more data, going to the modeling, complex modeling aspect to do a better job in terms of classification accuracy. We said, well, great, you now improve your model, we have more data, and you're using features which is MFCC and their suprasegmental characteristics, right? Question is, are these the best features? Is there any other feature that does better? And we have very interesting finding here when we let the network learn some features. So that's about this experiment. This we published last year again, 2020. So here what we did is we put a representational learning block, which is essentially one is CNN, but we put raw waveform. We don't put MFCC or their suprasegmental features. We put raw waveform. Let the CNN filter learn the right filters to extract relevant information. And of course, with batch normalization and max pooling, we did the representation, which we pass to 3 LSTM layers, and then followed by dense and softmax, standard stuff. Do a majority voting to get the classification out, right? So here again, the same set of data, didn't change the data at all. We just added the spontaneous, sorry, I think we added the image description task also here. Spontaneous was there last time. And again, same set of details that we do systematically in terms of how many layers, what optimizer, all of that. I mean, I don't want to go to the details because you can always ask me later if you're interested. And for the baseline, what we did was we used the MFCC as a feature, right? So we are trying to learn features. We have to show there's a benefit of this compared to the standard feature, which is MFCC, and on the same network. Now let me tell you what happened when we ran this experiment. So what you see here, we first run the experiment of ALS versus HC. So this is task-specific model, meaning you have individual task data, you train a model using that. What you have in 2 rows is the performance or accuracy using MFCC and raw speech. And whenever it improved significantly, we make that as blue color, meaning with raw speech, we improved significantly. But if we do not improve significantly, although average may be higher, we don't report that. So these no coloring means they're similar. They're not dropping. They're not significantly different. Okay, neither dropping nor increasing. So as you see, for here, image and DIDK task improved. In fact, we need to pool model, meaning you take all tasks together for training. But test time, you just do individually. Here, we get benefit using raw speech. So then it becomes a question that, okay, great. So if the raw speech-based features, which are probably different from MFCC, are doing better than MFCC, what are they? I'll just show you in a minute. Hold your breath. So here, PD versus HC, again, similar kind of stories we get benefit for almost all the speech tasks. Same for ALS versus PD. Here we did ALS versus PD, and we also get benefit in this task as well. Right? So here is the interesting part that we learned. So here, what we show is the for each of these three classification tasks. So let's start with the ALS versus HC. So for the task of ALS versus healthy control, we had, let's say, 256 filters. So the y-axis is the number of filters. And what you plot on the x-axis, one row, is the spectrum of that filter, which is like 0 to 4,000. And when you see a very dark red, like dark blackish red, that's the peak of that filter. They are typically band-pass filter. So you can see that the band, and they are sorted. We find the peak of this filter and then sort all of this based on the their mean location or the centroid of the spectrum. So as you see that almost all the filters are below 1000 Hertz. It is not MFCC. MFCC, as you know, they have filters all the way up to 4 kilohertz. But here all the filters are below 1000 Hertz. In fact, in particular, here we note it down, right? For the first test, which is ALS versus PD, it goes a little more, I'll say, up to 800 Hertz. But for PD versus HTC, up to 500 Hertz only, the max, the filter with the max centroid, the spectrum, that happens is up to at 500 Hertz. Similarly, for ALS versus HTC, it is at up to 400 Hertz. So there must be something in the spectrum that is in the very low frequency range that is good enough to tell the discrimination between this ALS and HTC. In fact, we presented this in one of the workshop on this, specific specific workshop, which we typically don't have these days, right? Because these are getting awareness is happening. They found it very, very interesting that this is at least breaking some of the standard way of seeing that MFCC and the MEL filters are always the best, right? Great, so far so good. Next, we ask the question, well, you have built a model, you have learned features, does better than standard features. Question is, you are doing everything in a laboratory condition. How about if we add noise? And how about we don't allow it to make such a very complex, several thousand parameters in an LSTM classifier? Can you still do any better? And this is something that we published this year in ICAST 2021. So there's a two questions. Can you show noise robustness? Can you show less complex model complexity analysis? So the idea is that we have to think of a feature. This is something that came out of our mind. That we asked, if you have to simplify the classifier, we cannot simplify unless you think of a robust feature, right? It's a trade-off. You dump the entire audio and learn it robust feature. That's one way. Another way is you think of clever features and have a simple classifier. And we worked in that route. And the observation that we had below 500 Hertz is mostly useful. We thought that there may be something to do with pitch. So let's just go ahead and use pitch. It's just single value, right? It's one trajectory, not MFCC like multi-dimensional trajectory, or even CNN learned features. So we take the pitch, right? And we estimate with swipe and payfac. There are some of the standard pitch extractor, which are noise robust also. So I just wanted to show you two examples. So this is a recording from all the patients in a clean condition that was recorded in the, and then this is white noise added at 0 dB. So this is your MFCC sequence. In these two cases, you can see what's happening to the MFCC, and this is a pitch sequence. You can see the robustness already, right? Pitch is much more robust than, or being invariant, I'll say, than MFCC. So what I said, well, if pitch is just such a simple one-dimensional feature and being robust, let's just go ahead and see whether pitch is at all discriminative for these classes, right? So what we did is we again fall back to CNN LSTM classifier with MFCC or pitch as the input. Now you see when it's pitch, we don't really need such a complex model. You'll see that very soon, right? So it's just a redrawing of the same CNN LSTM that we used earlier, not the raw audio, but MFCC as the input. So first of all, how do we quantify the complexity of the classifier? Using memory complexity, how much, model size, and runtime complexity, the number of floating point operators and flops recorded by the network, right? And we tune the number of layers, number of weights, all of that to make sure that we have three categories of network. One is low complexity, medium complexity, and high complexity. What does that mean? So here is a summary of that. So when you use a pitch as a feature, we use three complexity networks: high, medium, low, and the number of parameters are 55,000, 99,000, 2,000, or 3,000, right? So what are the networks? Yes, there is a convolution layer followed by max pooling, then LSTM layer, another LSTM layer, and dense layer, right? And it shows all the details of those to give this parameter. So what we are trying to do is we are trying to come up with a network with a certain number of parameters that matches with a network with MFCC also. So here you have number of parameters at 50 or nearly 55, right? Here is MFCC as the input. So again, you can see the network details, right? So we do the same thing. So we control the network complexity, right? Model complexity, and we use both the features. I hope that's clear now, right? So that's how we're controlling that. And then we said, well, how about noise? We did systematically now with white Gaussian noise only. In fact, we have run with other noises as well. In fact, 7 or 8 types of noises, and findings vary with noise. In particular, is worse with babble noise, as you know, because it's speech-like, and it's like babbling. I don't know whether this is similar to babbling, because when they have severe patients, they are probably, not natural, crisp speech. So at this point, we worked with reported with Gaussian with 4 different SNRs, and we did 2 conditions where we have a training test matched noise conditions and training test mismatched noise conditions, right? Here are the results. So what you see on the top is the ALS versus HC. What you see at the bottom is the Parkinson's disease versus HC, right? So first of all, we have used two pitch extractor, right? Swipe and pitch. As you see, the violet color is better than the green all the time. So swipe is much better, first of all, right? Then look at something very, very strange. So pitch is a single dimensional feature. MFCC is 40 dimensional features or 39 dimensional features. And compare this swipe, which is this brown and this red. In almost all the cases, they are pretty much similar. And look at the low complexity case. They are actually MFCC is falling down, right? And that's not surprising, because when you make low complex network, or not that complex network, but the feature has a lot of information, we have to extract that, and it's failing to do that, right? That's one finding. Then, as you see, as we go and decrease the SNR, meaning have more noise, both the pitch, the violet color drops, the red color drops. But as you see, violet is, as you go further from clean to 0 dB, pitch is more robust, because as I showed, right, pitch registries are not changing that much. And that was true for mostly both the ALS and PD cases. I hope that gives you an idea, right, that pitch by itself is provides a very important clue. Now, note one thing. I'll tell you we observe this. What is the trick here, or what is actually happening? What happens is, because these people are speaking slow with a lot of pauses, the pitch pattern changes. It's not single value of pitch, but how the pitch is changing. The CNN will capture that. So there'll be pitch, again, there'll be a lot of gap, pitch. But if you're healthy, you'll have a lot of different structure in pitch, right? Speaking rate will contribute to that, for example. And again, this is a result from a matched case. Similar kind of observation. You can see it's drastically improving compared to the MFCC, the matched case also. And the previous one was, let me see, I think I made a mistake. This is a sorry, there's a typo. This is a mismatch case where it's drastically. So particularly the mismatch condition, pitch is even more robust, right? So this was a match case, what I explained at length. The next one is a mismatch case, and that does really great. So that was quite exciting. That, well, I mean, pitch is so much robust. So why don't we think of then asking probably the muscles that contribute to this vocal tract, or sorry, vocal cord, and the muscles that contribute to the vocal tract movement, right? These two are different muscles. Maybe they are damaged in different ways, right? And then one may reveal more information than the other. So he said, let's look at source and vocal tract characteristics separately and see whether we can compare and tell them which one is more robust. And this is again a last interspecies this year. And essentially the idea was 2 main questions: that which source or vocal tract features are more better, and how much they are complementary. That's the main 2 questions. Again, we in this case we could manage to do complete the experiments for that paper in PD corpus only. Again, these are the 3 tasks that we used, and we use this kind of features. So for representing source, we just use pitch because they're easy to extract. For vocal tract, we used what is called voice removed MFCC, or voicing removed. So we remove the voicing so that the pitch is not present at all, right? And then we can take together source and vocal tract. That will be standard MFCC. So pitch, VR MFCC, and MFCC. So how do you get VR MFCC? So we do it through, word analyzer, where we break this signal into spectral component and the voice component, meaning pitch and periodicity component, and then we make the pitch, we make it 0 and synthesize back. So we remove the pitch. So it's like a whispering kind of sound, and that the MFCC from that whispered or de-voiced pitch will be called VRMFCC. As you can see, the dimensions of these features, right? Pitch is estimated using swipe because it was shown to be shown to be better. MFCC will be 39-dimensional, computed using Caldi, and these are the temporal values that we use. And these are the experimental schemes that we use. So we have the same classifier, by the way, right? For MFCC or pitch or VRMFCC or their combinations to find out their complexity, right? And then you see these are the various feature sets and the number of parameters. So we kept the parameters high, right? The complexity high, so that all models are equally compared. We are not giving undue disadvantage to MFCC or any such, because MFCC will be high dimensional. It requires complex models in order to see what happens. So number of flops are also all sort of comparable, right? Let's go forward. Again, same set of details of the experiments, but here we have used multiple noises, as you see, with 4 SNRs, match and mismatch training test conditions. First question was, is source better or vocal track better, right? So F0 versus VRMFCC. And we found that for some task, one is better than the other. And in fact, the best performance was from pitch in this spontaneous. As I just said, the speaking style captures, and that is the highest accuracy compared to all other tasks. So spontaneous was with pitch, and spontaneous combination was the best. Then we asked the question, well, are they complementary? So first we did a comparison of MFCC and VRMFCC. Whichever is significantly different, we mark them with hash. So here there is no significant difference. Here it is. Here it is. So spontaneous and DIDK task, MFCC was better than the VRMFCC. So it says that presence of pitch information, which is there in MFCC, not in VRMFCC, is actually useful. Next, we said, well, let's combine F0 and VRMFCC, right? And we find out whether that combination is better than individually VRMFCC or F0, right? So this is like taking pitch and voicing removed MFCC and asking whether when you combine them, is it better than the individual ones? And whenever you see both star and triangle, it means it's better than both of them. Otherwise, it's better than one of those. So as you can see, the highest performance came at 90.36 in spontaneous again, at the presence of pitch. You see, only pitch gave 88, right? And it's a little more than that. So that means pitch with something from vocal tract actually does really good. So they are complementary, right? And we did various other kinds of fusions, and we got and established the fact that they are complementary almost for all the tasks. Okay, I'll just move on for the sake of time. In fact, with noise as well, the same finding for different kind of noises together showed that pitch is robust compared to other features. With that, I'll come to the end of the presentation, saying that, as I said, we have now developed this app to some extent. I'll say this is a first attempt, right? It's not the final one. We try to make things gamified so that it's more like it's a game. So they don't just speak pa pa pa, but we have some kind of rocket going. As you speak fast, it goes fast. If you speak slow, it goes slow. Like that, you try to speak. So gamification actually helps to a big extent. And so we are trying this out with these patients. But I'll be happy, if you're interested, to collaborate, to find out people, and do something together to really make this happen for the people of this kind of people in our country. And there are a lot of people, by the way. The neurologist and the pathologist tell me that they work from morning 8 to evening 8. It's just enormous crowd. But primarily because there is not many good hospitals which are cheap like NIMHANS. NIMHANS is government funded, so there are a lot of subsidies. So poor people come there. So to conclude, as we understood that the agnostic articulatory characteristics in dysertic speech needs to be analyzed and understood, right, in detail. We know, just scratch the surface. There are a lot of things to understand. And we need to develop technologies for patients with dysertia, because they need this help from engineers like us. And we have to all work together. We have to bring awareness and work together to improve the quality of their life. With that, I'd like to acknowledge all the students, project personnel who have been involved in this project so far and currently are involved, and doctors, and finally DST for their support in this one. With that, I'll stop and I'll be happy to take questions.
Sir, I have a question.
Please go ahead.
Yeah, sir, in case of normal speech, when we extract the feature, we take the frame of 10 to 50 millisecond. While in case of slur speech, the speech is already very slow compared to healthy speech. So can we take the frame length more than 100 millisecond or 200 or 300 millisecond? It will be, means, is there be any significant impact on classification? If we
Good
take,
question.
yes.
Good question. So you don't do that because you don't know which person is slow to what extent. So what, if you have observed, we have done again at 20 millisecond, right? But now we are taking a supra-segmental feature, meaning you compute at 20 millisecond, but take, let's say, 100 of this. And then it will be 200 millisecond. Then you compute some statistics of these features. So if it is a healthy, there will be a lot of changes. But if it is dysarthric, it will be minimal changes. That's what is the key to capture their variation over time.
Sir, I have a question.
Please.
Suppose someone is affected from Parkinson's disease, and there are two voice samples. One is a healthy person and other is Parkinson's affected disease people. Then how we can identify that that person is affected or not with the help of cough?
Okay, good question. But I think this was the whole purpose of what we are trying to do, right? We are trying to get a recording from an individual and tell whether that person has Parkinson's or not.
Yes,
so,
sir.
Right? So the classifiers that we built for Parkinson's versus healthy control are towards that. Now, whether it can be done with cough, I don't know, because we haven't done with cough. In fact, making them cough is not easy because their muscles are not easily controlled. Like if I ask a healthy person to cough, they will easily cough, but not for these people. You have to be extremely careful handling these people. And ethics in particular is very, 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 very strict. And we need ethical clearance for all of these recordings. So cough, we haven't tested, so I can't comment.
Sir, one more question, sir. Sir, suppose I have a voice recording, sir, and I want to identify the Parkinson's disease affected people with the help of MFCC and LPC features. So what should be the procedure, sir?
No, see, as you have seen in our CNN team network, we have used MFCC and we have got decent result, but within this group, right? Of course, unseen subjects. So you can use, you can try LPC, but we tried LPC, we didn't get much benefit compared to MFCC. In fact, they are worse. What you can do is, this is my suggestion, if you try, it will be good to model their temporal characteristics. That is what we are doing with this CNN. So you stack up the MFCC features, let's say over 100 frames, and then run it through a CNN network to learn the temporal dynamics and then pass it through an LSTM network. That way it will be capturing the temporal sequence of the suprasegmental features. And that is what we found to do work well.
So, sir, a feature-based application is better, or machine learning-based application is better? For
As you saw, it's a mix, right? As you saw in my presentation, I hope you are till the end. See, we have found now the pitch, which is single dimensional feature, which is doing almost equivalent to MFCC, in particularly in noise. So we believe that it is don't need to be, I mean, I personally believe, I mean, I don't know about others, machine learning is great, but if we use blindly machine learning, I don't think you will gain benefit. We have to pay attention to the structure of the problem, the nature of the problem, the intricacies of the problem, and exploit that and put it in the network, right? We are using still CNN LSTM for pitch, not SVM DNN, because that does better. But the feature is cleverly chosen now because we found that pitch is more robust.
And which will give more accuracy, sir?
So far, we have found pitch plus, MFCC does better, best so far compared to pitch and MFCC alone.
Okay, sir. Thank you, sir. Sir, can I get your contact number and email ID if regarding that I will be having any problem?
Yeah, you can always drop me an email, right? I mean, I'll be happy to reply. You just drop me an email, Google first my name, you will get it. Otherwise, you can search with my lab name, Spire Lab. I think I put that up. Let me see if I can. Yeah, so you can write in this email ID also spirelab@e, or you can go to Spirelab and find my details and write to me also, no problem.
Okay, sir. Thank you, sir, for
Thank
giving
you.
this thing.
Excuse me, sir. Sir, we have a problem that suppose we have a normal healthy person and he is also speaking slurred. And there is a person with non-healthy which is having a disease and he is also speaking slurred. So how do we classify between those two that it's a slurred speech from a normal person or a slurred speech from a patient?
Good question. See, we are not classifying slurred speech between healthy and patients, right? Beyond slurring, there are many other factors that are happening, right? So slurring is one such. So there are many others, including the change of formats, their speaking rate, pause style, there is spectral changes, right? As we just saw all of them. So we are not trying to just extract feature of slurry speech. I hope you get that, right? So there are various other things that are impacting the speech. Slurriness is one such, but not everything.
Okay, sir. Thank you.
So my question is like, how to extract how are you extracting these sound signals? Like just you have shown like the use of mobile phones and the computer, and after that you have also shown some sensors applied at the different locations. So what are the requirements of that particular, what should I say, like the sensing mechanism that you are using for, or the recording mechanism, like how to avoid the noise and other factors that you are getting the exact signal that is required for further processing?
Okay, that's a nice question. See, when you record, I'm talking about acoustics only now. When you record acoustic signal like speech,
Mm-hmm.
you should not, in fact, worry about how to record so that there is no noise. I don't think that will be the case if you want to develop systems for the benefit of these people, because they'll be using at their home and natural environments. What our goal will be to use commonly used devices like smartphone, that's what we have used, right? And probably augment them with added noise so that you get a good classifier and model speed. But while recording, you should not restrict any such. But at the same time, I must also tell you that for specific studies to understand to what extent their format changes, right? We should actually record very good quality recording in a soundproof room or booth. So that if you have a question which is scientific in nature, which requires you to have very clean recording, you must make provision for that with a very good quality, device and things like that. Now, if your target is not that, but to make some application or classifier to be given to many people, then you should not pay attention. You actually should collect from many people on, from many places, and then use to build your classifier. So if your question is on how to ensure that you get a good quality recording, use a soundproof room, use a good quality microphone. But when I say good quality, it's a good quality A to D converter, if the microphone should have. And make sure that there's a puff, anti-puff filter, so that there is no puff or pop sound that's coming out from these people, and you'll get a pretty much good recording. But when you go for sensor-based recording, that's a different style altogether. It has to be done in a very different environment and room. Can't be done in a regular, working condition. So that is a different thing altogether. And for that, you anyway get a good quality recording. You can't get it on this noisy condition, but you have to add noise later on.
Okay, and what kind of sensor you have used? You have.
Yeah, so the sensor we have used is, I can show you, in fact, let me see if I can show it on our lab web page. I hope you can see. You can go to the facilities called electromagnetic articulograph. So this is the device that we use. You can see the screen?
Yes, sir. Yeah.
Yeah. So this is called electromagnetic articulograph AG501, where you place, I'll just show you some pictures, you may get some idea. Yeah, you see here is a picture where you are connecting sensors to this person's articulators. As after that, they will start speaking. You see another person with sensors attached. Does that give you an idea now?
Yeah, but these are like wired systems. So, I mean, there might be the chances of getting very noisy signals, isn't it? Like,
Good question. No, I mean, you see, this is what we hear whenever we tell this for the first time. Essentially, recording with this is even more challenging, right? For healthy people altogether, right? So what we do is we attach these sensors and we don't record as it is. We have to let them get used to the system, and that takes 10 to 15 minutes. You have to talk to them naturally. They'll first salivate too much because things are inside, right? And of course, not very much intrusive, but still on the tongue, right? So that will cause a lot of discomfort for them in the beginning. But
exactly.
both for healthy people and for patient, we have to be very much patient, right? To make sure we get a good quality record. In fact, I must tell you something. To get 20 minutes of recording, we spend 4 hours. For patients, it's 6 hours. It is not easy experiment. These are very, very difficult things to do. Very, I'll say, a lot of hard work by the students and myself. I always be part of it because you see, there are a lot of accidents that can happen. In fact, that happened with me when I was doing at NIMHANS. In fact, they are connected with glues, the sensors. And if by chance you don't, so if they take your tongue out, they take their tongue out, you attach the sensors and make them be like that for 1 minute till you dry. We have small hair dryer to dry them. Dry the tongue. And there are a lot of things that happen. I mean, I've been doing this since my PhD days, by the way. And then what happens is if it is not dried and you take your tongue inside, your tongue can get attached to your palate if the gum is still there. And that's it. These glues are so super adhesive. They don't they don't get separated. It's very difficult. In fact, I had an accident where by mistake I didn't wear gloves and my 2 fingers got stuck. So they actually had to put a scalpel to cut. It was such a risky thing. So I always make sure I am there, right? And I know the pain in doing, collecting such data from healthy people, of course, from patients. And in fact, we give them good amount of remuneration for them to be part of such experiment. And of course, we have good amount of data from healthy people. In fact, we are releasing this data also very soon, these healthy people's data.
Okay, sir. Thank you, sir. Thank you so much.
So any other questions?
Hello. Sir, am I audible?
Yes, go ahead.
First of all, sir, I would like to say that it was a very, very well organized talk for me, and I had many questions, but throughout the course of this presentation, most of them you answered them through the course, and many thanks for bringing this to us. Just had a few questions. Firstly, there was the classification between ALS and healthy persons, where you took some articulatory features, right?
Yes.
So my question was regarding when you picked up those mathematical models, where you developed those features. So were these empirical models, or was there some intuition behind this, the way you structured those features?
For the features,
yes, sir.
For the features which are listed here,
yes, sir,
they are designed based on our study and observation of those movements from those recordings.
Okay.
So we observe that their velocity and accelerations are much different. Although they are, as you saw, right, they're speaking slow. So there will be a different set of velocities and accelerations.
Okay.
Hello, sir. Sir,
so just one more question. The second thing is, when you mentioned that classification between dysarthria, where ALS and PD and normal one was compared side by side, where you said that VRM FFCC was together with F0, that is pitch, worked better than MFCC itself, right?
Right.
I'm quite new to this, but I think I saw you mentioned before that VRM FFCC was nothing but the pitch information removed from MFCC. So how is it possible? I mean, I'm curious how it's possible that MFCC is not as good as the case where VRMFCC is working better with F0 than MFCC itself, because it's simply the combination of both those things.
Yeah, see, this is where comes the insight into it. So what you're saying is more like a layman's way of saying.
Okay.
Right?
Yes,
so
sir.
we are not taking two features and stacking them each other, and that's not MFCC.
Okay,
In
okay.
MFCC, when you compute, if you look at carefully, we compute male filter bank energies.
Yes, sir.
And that male filter banks mirrors this pitch information to some extent. Now, to what extent pitch information remains in MFCC is not very clear. And to what extent it gets distorted. That's first question. But here we are explicitly giving the pitch.
Okay.
So that it can allow to capture the pitch information very much, directly, which is not the case in MFCC.
Okay, so yeah, if I'm getting this correctly, MFCC, the pitch information is masked by the vocal tract features. Is that what you're saying?
It's
And when
not
we're
masked.
providing them separately, I mean,
no, I'll not say it is masked. It is lost. It is
okay.
embedded in a way that is not easy to recover. In fact, we have a paper also earlier, a few years back, where we tried to extract pitch from MFCC.
Okay.
And it showed that so essentially, let's say you have 40 filter bank energies and you get only 13 coefficients, you really do a bad job of extracting pitch versus if you keep all 40. So if you give all 40 MFCC, static MFCCs, then you certainly have the entire pitch information. I'll say you have, but these are using all standard 13-dimensional MFCCs where you lose the pitch information.
Okay, sir. Thank you, sir.
Thank you.
No problem.
Thank you, Dr. Prasant, for very nice, organized, and very new topic. And there are lots of information we observed here in this particular presentation. And even this topic, which is this Arthik-based speech processing, it was itself is a new topic and it's a very difficult topic also, as I observed, because lots of information for data collection is required. So thanks a lot for new ideas to share here. And I hope most of all participants will definitely get definitely write you email if they are interested and start working in this area. So thanks a lot. Thanks a lot for this. Thank you
so much.
Thank you for your presentation. So before that, I would like to take a screenshot. So dear participants, if you turn on your videos, we can take a screenshot of that. Yeah, participants, please turn on the videos. So we can take some screenshots. I think that's enough. So thank you. So thank you, sir, for giving us time for the session.
Yeah,
thank you very much for the invite.
Thanks a lot.
Thank you. Bye.
Bye. So participants, the session is over for today. We'll meet in tomorrow's session at 10 a.m. So we'll close the session here. Thank you all for joining this session.